For this video, I'm going to be going over something called summation notation, which is another way of writing a series for arithmetic or geometric sequences. So the summation notation has several parts to it. It's the same idea of wanting to express the sum of multiple numbers together, and the abbreviated way of writing that is to use this notation where we have a series of symbols and numbers to fill in. First we have the Greek letter sigma. This kind of looks like an E piece here. This is the capital letter for the capital Greek letter for sigma. We also need a formula. This is often an explicit rule for either an arithmetic or a geometric sequence, but it could be a unique formula or a pattern that you might be able to figure out on your own. There's the index, which is which variable are they using essentially. So a lot of times it's going to be an I. Sometimes I see K's from different textbooks. And then the other two numbers that are important here, this is going to be the first number that we plug in. Most of the time it seems to start from 1. So usually you're going to start off by plugging 1 in for I, and then you would plug in 2, and then 3, and then 4. So this is the first number you plug in, and then you keep plugging in all the integers greater than that until you hit this top number. So this is the last number that you plug in. So you would stop when you plug in 5 in for the I value. And then since this is still dealing with series, we would add all of those individual terms together. So let's look at an example together here. For a specific setup, I have the formula 5i minus 1. My index is I, and I'm going to start off by plugging 1 into this summation notation. So if I plug 1 in here, I would get 5 times 1 minus 1. Well, that's 5 minus 1 is 4. And then I would plug in the next integer. So now I would go to plugging in 2. Same formula, 5 times I minus 1. Well, this is 10. Minus 1 gives me 9. And then 5 times 3 minus 1. That's 15. Minus 1 is 14. And then this is the last number I'm going to plug in. That's the number indicated on top. I'm going to stop after I substitute in 4. So 5 times 4 minus 1 gives me 19. Now remember, the idea on this is that we're actually adding those terms together. So this is saying 4 plus 9 plus 14 plus 19. So actually evaluating this summation notation, I need to make sure I remember to add those numbers up, which is going to give me my final answer of 46. So this is just a nice, concise way of writing these numbers added together. Of course, we could have changed some of the values around. I could have had us plug in up to like 30. But then once it starts to get to a larger number, that's where you probably want to go back on using the summation notation, the series formulas that we did in an earlier video. Let's look at a second example here. Sometimes they will ask you to find specific terms using the summation notation that they've given you. So in this case, they want me to find what the first 3 individual terms are, and they want me to identify the last term, and then still find the sum of those. Now in this case, they have indicated that it's a geometric sequence, so this might be a good one to actually apply the geometric series formula, which I will go back to when it comes up. But first, let's find the first 3 terms here. So I'm going to have 3 times 2 to the first, and then I'm going to have 3 times 2 to the second, and 3 times 2 to the third. These would be the first 3 terms in the sequence that we normally call a sub 1, a sub 2, and a sub 3. Well, remember to do the exponent before you multiply. So in this case, I have 2 times 3 is 6. And then here I have 4 times 3 is 12. And then here I have 8 times 3 is 24. Now you can tell that this is a geometric pattern because it seems to be multiplying by 2 to go from one term to the next. Now we were asked to find the first 3 terms, but we were also asked to find the last term. Now when we're dealing with summation notation, finding the last term is just found by taking the number above the sigma and plugging that in for your index. So in this case, I'm going to be writing that a sub 8 would equal 3 times 2 to the 8th power. Okay, so 2 to the 8th power times 3 should give me 768 in this case, because 2 to the 8th power is 256, and then we're multiplying that by 3 afterwards. So now we've found the first, second, third, and 8th term, but they've also asked us to find the sum of the geometric sequence. Now, as a reminder, let's look back at some of the formulas we've covered earlier. To find the sum, I need to know the first term of the pattern, I need to know how many numbers there are, and I need to know that R value. This is a finite series, so we don't need the infinite series rule because we're only adding 8 numbers together. So it's a finite number of numbers. So do I know all these values? Well, we just found the first term of the sequence a moment ago. We know that n is 8. That should be the number on top of the sigma symbol. And we identified that the pattern was multiplying by 2, so I know that r is 2 in this case. So if I use those facts, r is 2, a sub 1 is 6, and n is 8, then I can now just plug into this formula. So I'm going to have the sum equals 6 times 1 minus r to the n over 1 minus r. Now again, a lot of times when you're dealing with series rules, you're going to want to rely on a calculator for this, and you need to be very careful about the order you apply the operations in. So I need to do the 2 to the 8th power part first, which again should give me the 256, and then I'm doing 1 minus 256. So what happens here is 1 minus 256 is negative 255, and on the bottom I have 1 minus 2 is negative 1. And then when we multiply 6 times negative 255, that's going to give me 1,530. But dividing by the negative number is going to flip it to give me a positive 1,530. So that would be my sum for this summation notation. Now, a lot of times what's actually harder with summation notations is when the question asks you to write the summation notation based on a sequence that they've provided to you. So a lot of times what this is going to require, you need to identify the index of summation. Like I said, most of the time it's going to be an I. Sometimes you might be asked to use a K or another variable in the problem. And identify what the starting number is. This is usually a 1. That part will go underneath. So you should have something like I equals 1 or K equals 1. It's very uncommon to have a different number there. Next, we need to find the formula or the explicit rule. This is generally the hardest part. So you might need to figure out the pattern on your own, or you might be able to use one of the explicit rules if they specify that it's an arithmetic or a geometric sequence. And the last part is to determine how many numbers there are, and then that'll be the number that you put above the sigma symbol. So let's look at an example of when we're being asked to express this series sum as a summation notation. Now, to identify some of the information I have, this number right here, negative 17, that's my a sub 1 value. We also know the very last number in the sequence, so that's a sub n equals 79. And the other thing I would encourage finding is if it's a geometric sequence, find r, but this is an arithmetic sequence, so we want to find what the d value is in this case. So I noticed that they seem to be adding 6 over and over and over again. That's what's making this an arithmetic sequence. So by picking any number and subtracting the number in front of it, so 1 minus negative 5 or 7 minus 1, that's the easiest way to find the difference, and as long as it's the same number all the way throughout, then it is an arithmetic sequence. So this is what I have so far. Now going back to some of our formulas from earlier, knowing a sub 1, a sub n, and d, we should be able to solve for how many numbers there are in the pattern. And then if we needed to, we could also use the series rule to find the sum of all of them together. But let's start with solving for n. So I said a sub n equals a sub 1 plus n minus 1 times d. Now, if we were to solve this equation for my variable here, n, I would add 17 to both sides. So this is going to give me 96. I'm just going to flip the order of the 6 times n minus 1. Since multiplication is commutative, you can flip the order. 2 times 3 is the same as 3 times 2. My next step to get n by itself, you could distribute, but I think it's easier to just divide both sides of the equation by 6. So that would give me 16 equals n minus 1. And then the opposite of subtracting 1, we would add 1 to both sides of the equation. That would cancel this out and give me that n is equal to 17. So now we know how many numbers there are in total. What we were really trying to get, though, was the explicit rule. So if we go back to what the explicit rule said, so this is the rule right here, but we want to do it in general terms of n's. We don't want to have the specific numbers plugged in now. We want it to be in terms of n. So I'm going to write this a little bit differently this time. I'm going to write a sub n equals a sub 1 plus n minus 1 times d. So that is my explicit rule. But we actually could simplify things a little bit. Like I said earlier, we could have distributed the 6 through. So notice that if I distribute 6 times n and 6 times negative 1, that actually creates some like terms. So this could be combined as 6n minus 23 instead. So that's just a little bit more simplified, it's a little bit easier to use, and a lot of times when they're asking for the explicit formula, or any formula really, you want to try to simplify things as much as possible. If there are terms that you can't combine, do that in general. So let's write our summation notation now. So we have the sigma symbol. I usually start with that first because everything kind of goes around it. I am starting this pattern by plugging in from I equals 1, and we found that there are 17 numbers total that we want to plug in. So the number of numbers I have is 17, that goes on top. And then the last piece is we want to take that explicit rule, and then that goes right here on the side of the sigma symbol. So that here is our summation notation. It creates this series above. And then if we wanted to find the sum, then I would recommend using the arithmetic series rules shown earlier. But right now I'm just trying to focus on the how do you write the summation notation instead. So that's it for this lesson. I hope that was helpful.